Hey everyone, Freddie here, and I will be going over the third problem from this past January Gold Contest called Moo Route. So in this problem, we have Bessie, the cow, and she is located on a one-dimensional number line. So she initially starts at 0. So the number line could be like 0, 1, 2, 3, dot, 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 right? And she initially starts at 0.0. And she'll do a series of moves. So each move moves her one space either to the left or to the right. Right. So if she did the move right for the first move, she just go to space 1. She did right again, she go to space 2. And if she did left, then she go back, right? And all we know is that at the end of her path, she keeps doing this, and at the end of the path, she returns to location 0. Okay, she goes to back where she started. She might dance around over here, but eventually she's gonna come back. Okay. And Farmer Nodge wants to know her path, the path that she took, but he only knows that one, she never goes to the left of 0. Okay, so she always is on non-negative integer locations, and she never goes past n, where n is given an input. So she never goes to the right of some integer n. And additionally, Farmer Nodge is given an array A. Okay, and this array contains the number of times she's crossed the 0.5s. What does this mean? Well, she's gonna cross, right? When she crosses, or when she does a move, she crosses, these 0.5 markers, right? 0.5, 1.5, 2.5, and on, like 3.5 all the way to n minus 1.5, right? And so A of I will contain how many times that Bessie crosses I 0.5, okay, in her path. So yeah, so every time she crosses it, it's gonna just be one of those, just increment this thing by 1. So we're given the final array A, and we're given, right, additionally that she always stays between 0 and n. And Farmer Nodge wants to know how many possible paths Bessie could have taken. Additionally, he wants to know how many of these paths, or instead of knowing all the paths she could have taken, he wants to know how many paths she could have taken that minimize the number of direction changes. So a direction change is when, let's say, she's going to the right and then she goes left. Right, so she's like going right and goes left. Or if she's going to the left and then she goes right. Right, so it's a 2 consecutive LR or RL. Right, it's a consecutive, pattern of this or this. And if you look at her path, like let's say 0, 1, 2, look at her path, she goes to 0 to 1, then to 2, and then to 1, then to 0, right? The direction changes on these points, right? When she just pivots and goes opposite direction as she did the last move. So he wants to know how many paths that minimize the number of those. And we can go look at the sample inputs just to clarify the question further. So the sample input, n is 2, which means that Bessie will never go to any location more than 2. So she always can stay between 0, 1, and she's either going to be in 0, 1, or 2 for her entire path. And then the A array, A equals 4, 6. So she crosses 0.5 4 times, and she crosses 1.5 6 times. Okay, so how many paths are there that minimize the number of direction changes? Well, if you compute, if you like play around with it, you'll realize that she must change direction at least 5 times. And the 2 paths that she can take that minimize that have exactly 5 direction changes is these 2 down here, RRL, RRLL, RRLL. So I can demonstrate what it looks like. So R and R, then L, then R, then L, then L, then R, then R, then L, then L, like this. So that's her path. The second possible path is R, then R, then L, then L, R, then R, then L, then R, then L, then L. Okay. So yeah, these are the 2 possible paths that only direction change 5 times. Right? We can see how many times direction change each of the points is 1. So this is obviously 5, and the same thing for the second path. And she crosses, if you look at it, the 0.5 border is here. So she crosses 4 times, and she crosses this, the 1.5 border, 6 times. So these are definitely both valid paths. And so let's, going further, look at a not valid path, right? So let's look at a path that corresponds with the same number that has the same A array, and it stays between 0 and n, but it does not minimize the number of direction changes. So such a path would be, if she went R, then L, then R, then R, then L, then R, then L, then R, then L, and then L, like this. So if you look at it, she crosses 0.5 border 4 times and the 1.5 border 6 times, but she has 1, 2, 3, 4, 5, 6, 7 direction changes. This is a bad path. So what we want to identify here, right, is what distinguishes a good path from a bad path, and how can we just not count these bad paths? So look at it further, we can inspect what it means to cross one of the 0.5 marks. Well, she crosses it 4 times, right? But we know that she starts at 0 and she ends at 0, which means every time that she crosses the border, the 0.5 border, she has to go back, okay? So this 4 times is actually just 2 pairs of going to the right and going to the left. And additionally, these 6 times of crossing the 1.5 border is the same thing. So 3 pairs of going to the right, left, and right and left, right? So what is a different distinguishing factor between different paths? Well, whenever she crosses a border, right? Whenever she crosses the 0.5 border, she can have 2 options, right? Either she continues along and crosses the 1.5 border, or she comes back, right, and crosses the 0.5 border backwards. And so the different paths are basically when she decides to go backwards and when she decides to keep going forward, right? And additionally, when she's coming back, she can either, right, when she crosses the 1.5 border from right to left, she can either go back to the right or she can continue down. So these are what the decisions we have to make in order to create all the different possible paths. And so these 2 possible strategies is for the sample input. There are 2 possible strategies, right? The first strategy is when she crosses from 0 to 1, she can go directly back once, okay? And the second strategy is whenever she crosses from 0 to 1, she continues to go to 2, okay? Every time she crosses from 0 to 1, she continues to go to 2. And every time, yeah, that's it. Every time she crosses from 0 to 1, she continues to. She never changes direction at 1. Or she never changes direction when going from 0 to 1. She never goes this and then back. She always continues every time she crosses. So which strategy is the better strategy? And I mean, which strategy will result in the least number of direction changes? It's actually strategy 2. Why is that? Well, because let's look at strategy 1. With strategy 1, so we know that there are 3 pairs of up and downs for the 1.5 border, and only 2 pairs of up and downs, right, of going to right to left for the 0.5 border. So if he did this, if Bessie ever crossed the 0 to 1 and then went immediately back, well, now there's only one more going left, right, left, right? There's only one more pair of going from right to left and left to right. And so this means that whenever she comes back now, she has to continue on and then do the 6 crossings immediately, right? Because she can't go back, because then she's trapped here. She's trapped at 0. She can't ever go back because, right, she's already crossed the border 4 times. So she needs, on the second time she crosses this border, she needs to go to 2 and then do all 6 crosses of the 1.5 border and then come back. So this means that, right, this resulted in 2 extra turns actually, right? Because for the other strategies, right, they're like, if we look at again, they're like this, then this, and this, and this, and this. This is one of the strategies, right? So this only resulted, right? They combined 2 of the, or I guess it's not the strategy. That's one would be like this, and this, and this, and this, and this, and this, like that. Okay. So they combine 2 of these peaks together, right, into one big peak right here. So basically, we know that if the left-hand side, if the number of 0.5 crossings is less than the number of 1.5 crossings, this means that whenever we encounter this, we have to always, when we're going from left to right here, we have to always continue along here. Otherwise, we're going to make an extra 2 direction changes, right? Because the first strategy results in 7 direction changes instead of 5. So this is a good rule to have because it doesn't just apply for the sample input. It applies for every input, right? So whenever we have 2, we're at, let's say we're at position I, right? So this is like I 0.5, and this is I and I plus 1. Whenever when we have this position, and let's say it's I plus 1.5. Okay, if a of I plus 1 if a of I plus 1 is greater than a of I, this means that whenever we cross from left to right from I to I plus 1, we continue. We have to continue. We can't go backwards ever. This never happens. So we always continue forward because we don't have any direction changes to spare, right? Going backwards will just means that in the future we have oscillate one more time going up and back, right? So additionally, what happens if, let's say, instead of this being 4, 6, let's say it was 6, 4, okay? So she crosses the 0.5 border 6 times and the 1.5 border 4 times. So now what changes? Well, now we have 3 pairs of up and downs on the 0.5 border, right? And we only have 2 pairs on the 1.5 border. So this means that every time we're going from right to left, it's just the opposite, right? Every time we're going from right to left, we have to continue down. So every time we go from 2 to 1, we have to go all the way back to 0. Okay, we can't ever change. This never happens. We always have to go down, back down. Otherwise, we're going to create an extra turn. All right. So what do these pairings actually really do? It just means that these rules, the rules that we created, just mean that when we are going up and down, right, like this, whoever has less less pairs, right, less crossings, has to pair themselves with one of these greater crossing pairs, right? Pairing just means like, okay, so on the first, if the first guy pair with this guy, this means that on the first crossing, I extend here, okay? And if instead, if we had the first guy, if we had this thing pair with the second up and down pair, this means that only on the second crossing do I extend the entire thing, right? So you see this paired here versus in the beginning, the first would be pairing the first one like this, right? So you also have the less crossed border pairing themselves with the greater cross border. So in this case, for 6, 4, if the input was 6, 4 instead of 4, 6, how many possible paths would there be? Well, there are 3 crossings of 0.5, right? And 2 crossings of the 1.5, which means that, and we can choose, right? Each of the 1.5 pairs, each of these can choose one of the 0.5 pairs to pair with, right? So in total, there will actually be 3 choose 2 paths, okay, which is just 3 paths. Because there's 3 ways to pair one of these up and down directions with one of these guys, right? Because it's just 3 of them, you choose 2 of them, all right? The 3 choose 2. Now, what happens in the original input, right? Why? It's because, well, if we did this, it seems like the answer should be 3 here, right? Because it's just the reverse, right? The actual input is just 4, 6. It's the reverse. Shouldn't it be the same thing? Well, the answer is actually no, because let's see here. Here, I got to erase things here because I replaced them. If it was 4, 6, which is what it is in the sample input, and we had two up and down pairs here and 3 up and down pairs at the 1.5 mark. If let's say we paired these things like this, we paired this first guy, this first one, and the second guy to the second one, right? The third guy remains unpaired. This would just correspond with the path going up, right? Once and up again, then down and down, and then up and up, down and down, and then somehow up and down here, which leaves the path disconnected. And this is obviously an illegal path. So what went wrong? Well, it's because we had this extra lagging guy here. If we had paired this guy with this guy, then the path would look like this. Up once, twice, then come back down, and up, and down, and up, and then up, down, and down, right? Because he paired him with the last guy. And this middle thing didn't even matter, right? It didn't leave the path disconnected. So this just means that if the border to the left-hand side is less, the this corresponding index of A array is less than the next border, we have to actually automatically pair this thing with the last up and down. Okay, this is guaranteed. Like, it can never be that there's an extra up and down left at the end, right? Because otherwise it would disconnect the path. Okay, so instead of this being 3 choose 2, it's actually we just remove these two pairs. Okay, because they're fixed. We fix them. So it turns out that it's actually 2 choose 1, right? We have 2 possible up and down pairs, and we just choose one of them to pair with this guy, and the last one is fixed, right? So the answer is 2 choose 1, which is 2. Okay. So now we solve the case for if there's only 2 borders, right? So what happens if there's more than two borders? Well, this would mean, well, if we think about it, any border is actually not affected by the ones more to the right. So this guy, he actually doesn't care. Like once he pairs once he pairs up and downs, right? Once he pairs like this, and we create like some sort of pattern like this or something, he actually does not care what happens at these points, right? The guy can go whatever he wants, right? If there was more than 2, if n was more than 2, if n was like 4, if n was 4, then it still actually wouldn't matter, because he doesn't care what happens over here, because he knows that eventually whatever happens here, he's going to come back down, and in this case, the direction changes won't be affected, right? So if we were at the I.5 border, he actually does not care about the I plus 2.5. He only cares about the I plus 1.5, right? He does not care about I plus 2.5 all the way to n minus 1.5. He doesn't care about any of these. So they're like kind of independent events, right? They actually don't care at all. He also does not care about anything below him, right? Because once he goes down, every time he comes back down here, like here, it doesn't matter what happens. If something happens down here, he doesn't care. He knows eventually come back up, and so he can complete his path. So every single pair of 2 borders is independent of all the other pairs, or every single like consecutive 2 borders, I and I plus 1.5, are independent of the rest, which means that we can create some sort of DP, right? We can solve, let's have our DP be DPI means is equal to the number of paths where we only consider I.5, I plus 1.5 all the way through n minus 1.5. We only consider these borders. We don't care anything below it, and we don't care anything above it. And we already written out the cases for here, right? So this equals, we can write this out more formally. So we have 2 cases, right? So when we start from DPI, we have 2 cases. If A of I is greater than A of I plus 1, right? The number of paths for the current one is just n choose, no, it's not n, it's A I over 2, right? Because there's I over 2 possible up and down pairs, right? Choose A I plus 1 over 2. Okay, this is how many paths there are for the current one. So we would just set DPI equals A of I plus over 2, choose A of I plus 1 over 2, multiplied by DPI plus 1, right? Because we don't care anything to the right. It happens. We don't care what happens at DPI I plus 1.5 all the way through whatever. We only care about our current, right? Our current one. So this is that. And for the second case, right? Otherwise, which means AI is less than or equal to AI plus 1, then we would do DP, or I guess this could just be equal. I guess the equal doesn't really matter, because if they're equal, it's always 1-to-1, right? If it's equal, it's actually exactly one possibility. So anyway, DPI equals, right? We divide, right? We do the same thing. However, wait, I guess it's I plus 1 instead. However, right, we have to subtract 1 from each of the groups. So this is minus 1, and this is minus 1, because we're fixing, right, the last up and down to be, right, we're fixing the last of the I 0.5 up and down to be with the I plus 1.5 up and down, right? Because otherwise the path would be disconnected. So this is just our DP state, and then we're done. That's it. Our DP was very simple this time. It's just a little bit combinatorics. And so the last problem that we might have is doing choose, this choose function, right? Because if, right, we know the formula, right? A choose B or M choose N is equal to M factorial divided by N factorial times M minus N factorial, right? So everyone knows this formula. However, if we just brute force calculate the factorials, right? First off, they can be huge, right? Anything after 10 like anything after like I think 15 factorial is, or anything after I think 20 factorial is above integer limit. So we can't actually compute all these things out. Note that we just need to mod the number of, I guess we don't need to mod number of, wait. Yeah, we need to mod the number of paths by 10 to the 9 plus 7. Okay, so we can't actually compute the entire factorial. This can be done easily with like a factorial array where factorial I equals factorial I minus 1 times I mod the 10 to the 9 plus 1 plus 7, right? You can just pre-compute all the factorials. However, division gets a little tricky, right? Because when you're modding by a number, dividing is not the same, right? Because yeah, just for number theory, you can't divide once you mod by number, right? Because even though M factorial is indeed greater than this denominator, M factorial mod 10 to the 9 plus 7 might not actually be greater than this denominator. So you might get like some weird fraction that doesn't really make any sense. So you have to do something, you have to use Fermat's little theorem. I'll show you the code, but yeah, this should definitely be in like in the back of your mind, because there's a lot of questions that when you're doing modular arithmetic, you need to do inverse, because so basically instead of dividing by the denominator, you multiply by the modular inverse of the denominator. Okay, so instead of dividing, it's actually you do M factorial multiplied by this denominator to the negative 1. All right, it's just like modular inverse, and it's the equivalent to dividing. And the way you can compute the modular inverse is with Fermat's little theorem, which is like the theorem that like n to the p minus 1 is equal is 1 minus, or n to the p minus 2 or something. Let me check the code. But yeah, just Fermat's little theorem. Here it is. Yeah, n to the p minus 2 is congruent to 1 mod p. So the modular inverse of n with respect to some mod, which is like 10 to the 9 plus 7, is equal to, if you raise it to the power of p minus 2. Okay. And to do powers, we can't, right? Because p is 10 to the 9 plus 7, right? So you can't actually also brute force compute all the powers. You need to do a fast exponentiation, which I guess I'm not really going to cover here. You can look it up. It's very it's just doing exponentiating a number in log of the exponential time. So to take a number to the power of 10 to the 9 plus 7, it actually takes log 10 to the 9 plus 7 time, which is just around like 30 operations. And it's with this thing over here. It's just using the bits of the number. It's very common. So this is my choose function, right? So instead of, I have a modular inverse function, which is just from Fermat's theorem. But yeah, so n choose m is actually factorial, right? Fact is my factorial, right? So it's facts n multiplied by the modular inverse of m factorial and the modular inverse of n minus m factorial. Okay. And so this is the entire code. The code is actually very short. First I read in the A input. So in most of the input, the fact is just most of the code is just reading input and pre-computing the factorials. So this is a factorial array. I'm just pre-computing it. And then here's my DP transition, right? If AI is greater than AI plus 1, you just do choose AI over 2. This is exactly what I wrote. Otherwise, you choose minus 1. And yeah, that's it. And so how much space does this take? Well, the DP itself takes linear space, and yeah, n is around 10 to the fifth, so it's just 10 to the fifth integers. And the actual computation of the DP, I guess it takes n log n, because you have to do Maltese inverse, right, for every choose operation we do. So it's around n log n, so which is totally within time bounds. And then at the end we just print dp0, right? Because we just print, remember, dp I is just the number of paths with only counting I through n minus 1.5. So dp0 is just the entire path. So all we do is print dp0 at the end. So this takes like basically around at most 1 million operations, maybe like 5 million operations. So it's definitely within time bound. And it's very short and sweet. So yeah, this is just a very classic combinatorics type problem. So thanks everyone for listening.